Hey, good afternoon, Twitch family. How you doing? I'm here to bring you some new content. And what are we going to be doing today? Well, we're going to be building a clock, a system clock to be precise. And this is going to be for our 8-bit computer that we're going to be building. This is going to be a series of videos as we go ahead and build this 8-bit computer. But in order to get the computer running, we need to have it be able to do things at a synchronized, constant pace. And that's where our clock comes in. This clock is going to tell the computer and the CPU when to go ahead and activate and do a process and end it and give it a window to work it in and update at a set scheduled time. So, so we need to build something that's going to allow it to do that. So you're probably wondering, like, well, what is a clock? A lot of you might have watched these YouTubers or just looked about getting computers and heard of overclocking. Essentially what they're trying to do is they're trying to make the clock in their computer run faster, turn on and off at a faster rate, so it can do more tasks in the same amount of time as it would if it wasn't overclocked. So let's take for something a little easier to handle instead of gigahertz. Let's talk about 1 hertz or 1 second. So every second, the computer will be able to do a task. Transfer bits from one register to another, or transfer bits from one register to the ALU, which can do math and solve problems or do something and compute something that we want. So every second it can do one thing and then complete it. So 1 second it transfers something, the next second it adds to it, the next second it then throws it into another thing. So this is all done at a certain pace. Well, what if you were able to do, instead of 1 second, you were able to do it every half second? So you basically doubled how fast the computer can do it. So every half a second it can transfer something, every half a second it can add and do it. So now you transferred something to your ALU, it calculated it and spit it out in 1.5 seconds instead of 3. Well, what if we could even do that, make it faster, make it like 1/4 of a second, or an 1/8, or a 1/16 of 32nd, milliseconds, microseconds. And this is what the system clock can do. And it all depends on what kind of hardware you're using, what kind of chips you have, how fast can they update and populate information through it, is basically how fast you can push this clock. Because theoretically, you could have this clock turn on and off infinitely amount of times and in a given time frame, and so it can do everything instantaneous. In theory, it doesn't work like that in real life, sorry guys. But that's essentially what a clock does. Now you probably heard me say, we want to know how fast it can do it in hertz or period. Let me give you a little diagram of what we're looking at here. So here's an oscilloscope, and this is taken off of my oscilloscope on the clock that I had built, and it shows you and calculates out your frequency and period. You actually can see here it would show those. Let me hide my face real quick. Whoop. So right here you see period is 1 second, frequency is 1 hertz. Those are correlation to each other. Hertz is 1 over the time. That'll calculate your hertz there. So 1 over 1 is 1 hertz. So what a period is, in graphically showing here, is I don't think I was showing you. I am sorry. I was pointing at the wrong thing. You didn't see. Here's our period, our frequency. I'm sure it was pretty obvious, but I'll point to them. So this is our period and our frequency. So for our period, let's think of a circle. Let's say you're going to run around a track or walk around a track, and it's a circular track. And you're starting at the top, and you run around it, and you get back to where you were when you first started. That would be considered 1 period. 1 cycle has been completed, and you can visualize this here. Let's look at the starting point here. This is where it went high, and this is 5 volts high, and this is 0 volts low. So it goes 5 volts, turns on, then turns off, and stays off for half a second, and then turns back on. So in 1 second, half a second here, half a second here, it went from on to off and then came right back to on. So every second it'll rotate from on to off, on to off, on to off. And you kind of think of that as a circle. So that's our output. This is a nice square wave. It comes up, turns on, turns off, and makes a nice square wave. This is a good clock for your computer to know when to do something. Very slow, every second it turns on. So like this would be an edge. This is your on edge. So every time it hits here, it senses that it went from from low to high. It says do your operation. It does the operation, it does everything it can do until it hits here, and then it needs to start a new cycle. So from this point here to right before it gets to here, it needs to complete everything in that cycle. Now for 1 second cycle, it has completed, and now it's just waiting. Because computers are very fast. For us, 1 second's not much time to do anything. Now, what we're looking at here in blue is our capacitor. Now what our capacitor does is that it gets the high voltage and it charges up. Charges, 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 and at this point right here, the power is cut to it. And so it slowly discharges, losing its charge. Going down, going down, going down. As you can see, it never went fully down to 0 before it comes back on again and it starts charging up. Charging, 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 discharge. Because this is when we have 5 volts, this is when we have no voltage, so it starts losing it over time. Capacitor is like mini battery, you can think of it as. It allows you to hold voltage and keep a charge, but then as soon as it starts losing and dissipating, it goes down, 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 down. Now, as engineers and people who design circuit boards, we can use the time coefficient of a resistor and a capacitor to figure out how fast we can have the discharge and charging take place in the capacitor. And that's tau, and that's basically 1/3. But we'll go into more of the math here in a little bit. So by using the capacitor and the resistor and a little bit of math, we can figure out, hey, how often can this turn on and off? And we will use a 555 timer for that. And this is our 555 timer. It's a little IC chip. It's got an input VCC. It's got ground. It's got trigger, output, our threshold, reset, a bunch of things. And we'll go into a little bit about how we're setting it up. But using this chip and the resistors in series and a capacitor, we can kind of calculate how we want our output to go, and which is really good. And then that'll give us this signal on the oscilloscope, which is nice. So let me show you a quick little diagram of what we're going to be looking at for our clock. What are we going to be building today on our breadboard and seeing this LED turn on and off? Well, that's this right here. We're going to need 3-4 things for it. We're going to need our capacitor. We're going to need a couple of resistors, an LED. That's really all about what you need. Of course, breadboard and power supply and that kind of stuff. But so what are we looking at here? Let me get rid of my face. Sorry, guys and gals. This right here in this box, kind of outlining it, is our 555 timer. Essentially what it is it's 3 resistors, and as the voltage comes through the resistor, so you have 5 volts coming in, it gets a voltage drop across the resistor. Each resistor has a voltage drop. So if you were to probe at this end and the ground, you'd have a certain amount of voltage between this resistor and this resistor. Put the positive end here, and at the ground you'd see another voltage. So you wouldn't have exactly 5 volts as it goes through the resistors. So what's happening here is we have a couple comparators, and basically what they look at is, hey, we got positive voltage coming in and a negative voltage If one is higher over the other, it activates and lets a signal out. And if the signal comes out, it goes through this SR latch, and we will talk about digital logic here soon. So don't worry about this today. Just know that it goes through a couple comparators, goes through a latch, comes into this transistor up here. When the voltage comes through it, it opens the gate, which allows the voltage to come down and ground. And then that basically is when it cuts off the power, is when the gate gets power. When the gate doesn't have power, it gets chopped off here, so there's no voltage coming in, so this transistor is no longer working, and that allows the voltage to travel through these resistors outside the chip and the capacitor. And so it's either coming in and grounding out here, or it's coming on back up and then grounding out here, and it's just working with the IC chip here. And then this is our output. This is our clock output right there. So let's see if we can get a little more of a circuit here. Yeah, that's right. Here's the simple formula for how it's going to be. We have our tau high and our tau low. Again, I was talking about duty cycle for how long one's on plus how long the other's on. Gives you your full period. It doesn't have to be 50-50. You don't have to have it high on for half the time and low on half the time. Maybe you have high on for 80% of it, and then it just drops low for only 20%. But still, that gives you the full 1 second, or microsecond, or whatever your period's going to be. And this is your calculation for it. The 0.693, consider that like a coefficient for how the 555 timer works. And then you have your resistor RA plus RB times your capacitor. And so here's RA, RB, and our capacitor. So we calculate as it goes high, because it goes all the way through and utilizes both of them. And then for our low, when the transistor turns on, it only comes back through RB. RA has no effect on it, because now the current flow comes up this way because it wants to ground out, because you have all this positive voltage on the capacitor still on this side, and it needs to go somewhere. Well, it's not going to be able to go this way because you don't have it going there. So it comes back up, comes through here, and then grounds out, because now you have your ground connected. So it allows it to discharge, and that's that really cool. What was that part here where it comes down and discharges? So you have your charging, which is capacitor or resistor A plus B times the charge. That's how long it takes to charge, giving you your on. And then your discharge, which is RB times the capacitor. That's your discharge rate. Adding those two together gives you your period, which for us is 1 second, 1 hertz. Alright, so hopefully that helps. Now, I know I don't have any viewers or anybody at the moment. My channel's so new, I don't have social media, and I'm really expecting that it'll pick up as people see it on YouTube or wherever I store this. But in the meantime, I'm going to try to answer those questions and go at a pace that I think anybody could follow. And eventually, when I do get viewers, you could be putting your questions up there in chat, and we could watch it, and I can answer them. But yeah, so here's our equations right here. This is what we're going to be. So if you put it in 1k ohm and 100k ohm, add those together, and multiply it by 1 microfarad, you would find you get your answer. Add those two together, you get your 1 over 1.44, which is your coefficient for the IC chip, your RA plus 2 times RB, because it goes through it twice, times C to get your frequency, which is essentially your period, this over your period. So this is how the math checks out. Add it all together, what you get if you had it set up with that exact thing. Now, this is a percent error calculation, and we can kind of go over that a little more later. If you want to find out how exact it is, what your measurement is to your experimental result, and that's really good when you're starting to do scientific experiments. You kind of want to know, hey, I calculated it out using this formula, but on the oscilloscope, I'm not getting that. How much am I off by? Can I calculate why I'm off by that? And I'll tell you, one of the biggest things is because a capacitor never has the exact capacitance. It could be off by up to 20% in some cases, depending on the capacitor you're using. And that same thing for resistors. Some resistors are really good. They're only off by like 1% or even lower. I don't know if you heard that, but that was my pup. She's down there itching her nose. Oh, Lily. And so when you plug it all together, they start playing off of each other and start giving you different values. But yeah, so anyways, these are just calculations that I've done. Here is our actual circuit that we're going to be building today. This is going to be having our output, and this is our 555 timer here. We got a capacitor C2 here, which essentially is just going to try to make it to where we don't have any fluctuations in our voltage, that we always have this real nice good constant 5 volts coming in supplying the chip, which will help to make our actual output voltage to be more of a, say perfect square wave as much as you can. We have we have this basic setup here now. RRA and RRB are going to utilize two different resistors. We're going to still have a 1K ohm resistor here, but we're going to give ourselves the ability to have a variable resistor or potentiometer, depending on how you want to say it, as our RB. Because what we can do when we put this variable in is we can have it go from like no resistance to max resistance, and see how that changes the clock when we have it. And we can watch that with either you can watch it with your LED, turn on and off. It might blink faster or slower depending on how much resistance you give it. And so you can kind of play around with that and then see how that works with your math, and if you're getting what you should be getting on it. But we'll go ahead and kind of leave that up there so you can kind of see what we're going to be building today. Before I show you the calculation I did for 1 second, let me put the formulas back up here for you. Right here. We have our period and our frequency. Can you calculate giving 1 microfarad? Now, a microfarad is 10 to the negative 6, if you're calculating that out. For those who are not math savvy, don't know what that is, let me show you here. So, I might need to change up how the webcam works, but so this is the symbol for microfarad. You have this weird little U, and this U stands for micro, and the F is for farad, and all capacitance is rated in some form of a farad, which was actually by the person who discovered and created it was farad, so if you look into them. Anyway, so a micro is 10 to the negative 6. You might have seen something like that before. Some of your math classes. If you're younger, you may not have ever seen that. But essentially, this is equal, if you write it out in decimal, 0.00001, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6, yeah. So if you were to bring the decimal out 6 places, this is what 10 to the negative 6 represents right there for you. So if we have a 1 microfarad, here it is. That would be 1 times 10 to the negative 6. And there's our 1. So that's 1 microfarad. So when we're dealing with things. Now you might see this symbol. That's ohms. That's resistors. All resistors are based off of ohms. You might see something that says like, I have a 10 ohm resistor, or I have a 1K resistor. Sometimes they'll include the ohm symbol, so the 1K ohm, or they'll just write it as 1K, 2K, 10K, 100K, whatever, and all numbers in between. So that K represents this. That equals, followed by 3 zeros. So let's say we had a 42K written there. Well, what's that equal? Well, what you do is you put the 4, the 2 there, then you follow it by the 3 zeros. So that'd be a 42,000 ohm resistor. Does that make sense? It just makes it easier to write it with this instead of writing it out like that. That takes up a lot of space. It's easy to make mistakes if you have a bunch of zeros. Let's say you had like a 2 million ohm resistor. That would be written like this. 2M per million. Makes it a little easier. So K, 1K, 1,000, M for million, and that's kind of how it is. So when you're doing your math with your resistor, if you have something that's, you have your RA plus RB times your capacitor, and we know that RA is 1K plus, let's say 100K, and then we had 1 microfarad. We could say that that's equal to 1,000 plus 100,000 times 0.12345 and you could start doing your math there. And then whatever this answer is, you can go ahead and do it out. So you have a 101,000 times 0.12345 and you could take away 3 zeros, so now you got 101 times 0.001 and finish that off. Calculate what you need to do. So anyways, that's how you deal with the different labels and calculations for the exponents that you find there. Some other ones you might want to think about here is milli. You might see something like milliseconds, which is 10 to the negative 30 seconds. You have milli, you have micro. What other one do we have? 10 to negative 3, 10 to negative 6. Yeah, those are the two big ones that you usually see. 10 to negative 3, 10 to negative 6. So, yeah. Anyways, I hope that kind of helps when we're dealing with these different numbers there for you to calculate. So, yeah, if you've been watching along, I'll let you go ahead and take a few seconds before I start up. I'll probably edit this part on YouTube. I'll put up the full video of it, but I might put up the calculation part separate so we can kind of do the math and watch it there. But I'll let you guys take a second and do your calculations. See if you can figure out what we need to do to get a period of 1 second or 1 hertz. So I'll put that out. So we want a period to equal 1 second. If you can get it to do that for 1 second, that'd be good. And I will switch you back over so you can see the formula. Before I show you the actual math that I did. Now, depending on what you select for your RA or RB, I kept 1K for RA, I made RB variable, and I kept C 1 microfarad. So I only had one variable to solve for. And if you've done algebra, that should be pretty easy. If you haven't done algebra, then you might be a little confused. So just hold off and wait and find out what you want to do. But I'll let whoever else wants to do the math go for it. I'll give it another 30 seconds. Come on, Lily, give him 30 seconds. I think that'd be good. While some of you finish up, do you want to see my puppy? Let's go here. Let's see if I can. I apologize. But there's my pup. Hi, Lily. How you doing, kiddo? You a good girl? Huh? You bored? Yeah. It's a good girl. I should get a puppy cam. What do you think? Should I get a puppy cam? Should I invest in another webcam for puppies? You can keep an eye on her. Alright, I think that was long enough. Did y'all figure it out? So let me scroll on down to my math. How embarrassing would it be if I did it wrong? I didn't. So, let's switch over to desktop view. Here we go. Here is our math. So, use the same calculations here with the coefficient of 0.693. And I calculated that I would need, oh, I see on this one. Okay, so your number might be a little different from mine, but that's not a bad thing if you use 1K exactly. I was using the actual voltage or the resistance and capacitance that I had measured using equipment on the ones that I did. That allowed me to actually get that right on dead center 1 hertz clock pulse. Anyways, yours is roughly going to be around 686K. 680K, somewhere around there, is what you're going to need for your RB to be, which is a pretty big resistance. We're getting near a million ohms at that point. And then you had your microfarad, and if you calculate that out, that'd give you about half a second, which is what you need if you want to do a 50% duty cycle. 50% high, 50% low. And that's your calculations. Add those two together and you have roughly your 1 second mark. See how it's even just slightly different though? Because your equations aren't 100% the same. That's trippy. So obviously you know that RB has to be the dominant force. You need to have RB be considerably larger than what RA is going to be if you want your two equations to be about equal. It has to have such a low impact in the overall scheme of things if you want a 50% duty cycle. And it's never going to be exactly 50% because RA is going to contribute something. Even if it's a very small amount of RA, it still will have a little bit of an impact, but in the grand scheme of things, it's pretty low. But you see, that's why this isn't 500, this isn't half a second compared to this one. It's off just minute. This is where significant figures might come into play if you're used to that. Like how far out do you go on your decimals and do your rounding. But yeah, so then we have another 1.44 for our 555 timer to calculate the frequency. And 2 RB because you have to go through it twice to go high and low. Times your capacitance. Calculate that out and look at that. You're looking at about 1 hertz. And then when you wire it all up, you see that you will have this setup here, and you'll see your capacitor charging and discharging, which is pretty neat. So we'll go ahead and keep that up on the screen. So what do you say we go ahead and start building this and hook it up and see if we can get the actual voltage and everything to show up. We'll use something called waveforms, and I should be able to demo it on the computer here. So let's go to circuit view, and we'll start setting it up. So we got the math behind us. We have the diagram. Oh, you guys probably want the diagram too, though. Well, you can, yeah, I guess that's not much I can do about that. The screen would be really small if I showed both images up there. So we'll just kind of focus on building it. You can build it with me. I should have been a little more prepared and had everything out here, but yeah, no biggie. There's our 555 chip. It's not very big. Yeah, try to. So you see it has 4 pins per side. Starting over here. That counts, that top pin's 1. It counts down, crosses, comes back up, and then that pin up there is pin 8. So that's how you calculate it. And I don't know if you can tell, but there is a little notch up there that signifies that that's the top. And a little dot. You see that little circle right there? That little circle and notch kind of tells you the orientation of the chip to know whether it's up facing straight or down. So that's that. And then if we go back to desktop view, you can see I drew out the chip with its pins in the appropriate way. That let me be able to figure out what I was doing a little better. So I'll keep this on the screen for you for a second so you can kind of see what you need. We're going to need a polar capacitor that's actually polarized. You might have seen those on different boards and things before. But we need a 1 microfarad version of that. And that's what one of these look like. Microfarad. You see right there, it shows that it's a little negative on the gray. This side that's facing the camera right here tells you need to make sure that this pin here, which is this one, is your negative side that goes to the ground. And they also made the positive lead longer. So you can tell the shorter one goes ground, longer one goes positive, also known as cathode anode, if you want to get scientific terms. Yeah, so you'll need one of those. You'll need an IC chip, a breadboard. You don't need a very big one for the clock. This one's fine. I'm sorry, the camera does an autofocus thing, so should autofocus on there. Gonna focus. There we go. Alright, so then what we're gonna need is the other capacitors. So we have 2 other capacitors. one that goes from pin 1 to pin 8, and that's just that's your ground pin, or your positive and ground input output, and that essentially is just going to allow that capacitor to give you a good constant voltage input, and depending on what you're using as your power source, it will be good to help out and smooth out anything, eliminate noise. For pin 5, we're going to go ahead and ground that one too, and that one doesn't do anything that we needed to really worry about at the moment, but we're going to do another capacitor there to help kind of remove some of the noise that the chip will have. It's recommended in the diagram here for the data sheet. Now, as you start working with electronics, I do want to make one thing clear real quick. Get used to seeing data sheets. Data sheets are key, and I have this one up here for you to look at. These are called data sheets, and what they do is they tell you everything that you need to know about the specific chip you're using. And I'm using the NP or NE555 timer, and this is everything that you need to know about it. It shows, usually it'll start off by showing you what each pin is, what the name of it is, how it works. Sometimes it'll show you one that's an actual one that can go into a breadboard, and then it'll show you a surface mount version of it, depending on if they have that as an offer. But yeah, and some of them have a little more ability, but we're focusing on our simpler one right now. And then it can come down and it'll show you, what voltage temps can it work out, what kind of tolerances does it have for current, how does it work, what are the functions of it. Here's a function table. If reset's low, it doesn't really matter what the trigger does or what the threshold voltage is, the output's low. Reset resets it. Yeah, you can see that. And if it goes high, what happens there? So the information in the data sheets are really helpful. Here's an example of how the chip works internally. It's pretty close to what you were seeing. You have a couple of comparators and a trigger. You have the 3 different resistors that are coming through, and depending on which one has the higher voltage, will activate it, and it goes through an example of a flip-flop and then has an output. And here's a transistor that'll ground out if the voltage is high enough or low enough. Scroll on down. Here's your max. So right here, 18 volts. You can actually put in a decent amount of voltage into it before you start damaging the chip. Your VCC input voltage is the same as your constant, your reset, your threshold, and your trigger. And all kinds of other information that you might be interested in. And as an engineer, you'll be going through and learning what all these different things on the datasheet tell you. Don't get overwhelmed. It is overwhelming, and some of the things on there, I'd even have to kind of look up to realize, well, what is that? What is it that they're talking about and whatnot. But it'll give you good information, and sometimes they'll leave, here's some graphs on how it works and heat and everything. But they'll even sometimes give you example of, here's a monostable clock operation. If you wanted it, we want astable, but yeah, it'll show you, like, hey, here's an example of how we use our chip, and give you good application information on waveforms and things that you can get from your oscilloscope. Astable, this is more or less what we're doing. This should look pretty familiar to you, because that's kind of what we're doing for it. And this is our output, and this is our capacitor charging over time, and how to calculate everything. Here's some equations. Those equations I gave you, came out right out of here, which is great. And this is what data sheets will give you. So if you're an engineer or thinking about becoming an engineer, get used to learning about how data sheets work, what information you can get off of them, because that'll make your life way easier. Anyways, put that back up there for us. So for our capacitor 1, C1, on our schematic here is we have 1 microfarad polar capacitor. Capacitor C2, C3 are going to be, what were they? They were 0.1 microfarad capacitors, so 10 to the negative 7, 1 times 10 to the negative 7 capacitance. So they're just little, just enough to keep everything kind of clean. You'll know that they use capacitors and resistors as filters to kind of clean up some of the noise that can be generated in circuits. And as we go on farther, you'll learn a little bit more about filters and what they do. But just know that it kind of cleans everything up. Pin 2 will kind of have a little splice. When you see a little dot here, it means that it's also connected. So it's connected here, comes down, and then connects up to pin 6. Pin 3, when you see this, at least on mine, that means that it's not connected. Think of it as just kind of like a wire going over. That's our output. That's going to be our out to our clock. This is how our clock is going to connect up to our computer. In this case, in reality, what we're going to be building, it's going to have a little more. We're going to make it a little more complicated, but it'll make it more fun too. You have your supply voltage of 5 volts coming in through your RA and your RB, which is our potentiometer. Comes in, and for pin 7, pin 6. Pin 8 is our supply voltage of 5 volts. So now these two can be different, just so you know. You can have like 18 volt supply, but maybe you have a, I don't know, 6 volt input. They can vary, they can change. It depends on what the operation is you're doing, and that's where the data sheet can come in and let you know, hey, this works or this doesn't work. It's all right there. Then pin 5 is grounded out through the capacitor, and then pin 4 goes straight to 5 volts. So let's go ahead and start building this. Let me show you the potentiometer for the circuit, so we know we have everything we need. So I'm going to use a 1 million ohm variable capacitor, or variable resistor here. That's that. And then last is our 1K ohm resistor, our RA, that we'll need there. Now, for some of you may never have used a breadboard before. Let's say that you got one because you wanted to follow along and you're building this at home, but you don't know how breadboard works, which is totally fine, because most of the engineers I went to school with, when I first started doing the electronics with them, most of them had no clue how a breadboard worked, which is kind of funny, because I was interested in this stuff before I became an engineer, so I kind of already knew what a lot of this stuff was before I went to school. Man, I couldn't imagine how much difficult it was for learning all this for the first time in class and doing all this theory and not even knowing how a breadboard worked. But anyways, so this is the breadboard. What you're going to usually see is you're going to see two ends that have red and blue written on there. You got a little plus and a minus. The way that breadboard works is that your negative, this is your ground, is all connected this direction. It's connected up and down. And that's the same for your positive, up and down. But it's literally not connected to the board. Has no connection. You see, I split that apart. It doesn't connect to it. And the other end, same thing. It's separate of it. So you don't have to worry about, positive and negative touching and grounding out and shorting your board. On the middle part here, it's labeled A through E and F through J. And they're connected. There also is rows 1 through 30. Yeah, row 1 through 30. They run this way. So these dots up along the top here are connected. The row below it is all connected this way, but it's not connected to any of them on the top. So if you plug in a capacitor or a resistor, let's show you real quick. Actually, this one will be a little easier. Let's say we put in our capacitor this way. Ooh, this is a new board. It's new. So, if you put it in this way, the two leads aren't connected together. They aren't touching. They're not shorting. Because this row and the one below it are not connected together in this direction. They're just separate from each other. But if you were to go and try to put it in like this, see how it's in the same row? Those leads are connected. They're put together. They're touched. This is a short. This is not how you want to do it. So it connects this way, not this way. So these are separate. The rows are separate. Now, this middle area here, and I am sorry that it does the focus. This middle area is your divide. So this side is not connected to this side. So a lot of times, what you'll see people do is they'll bridge the gap with a resistor, capacitor, LED, whatever. Now that is not shorting. That is literally bridging the gap. And so everything kind of goes through the capacitor in the right way. That is acceptable. So that's kind of how a breadboard works along there. So you can kind of follow along as I put it together. IC chips. They're great. Some of them are expensive, some of them are cheap. Now a lot of times you'll get them and you'll see that the chip, I already kind of bent this in. Let me see if I can find one. Hold on real quick. Yeah. Here we go. Here's two chips. So the one on the right here hasn't been messed with before. The one on the left has. You can see the one on the right here, they're bent out kind of far. That's manufactured that way. But they don't fit well into the breadboard. And most likely if you haven't done it before, you try to line it up, you'll realize, hey, wow, look at that. It's like really far apart. It won't fit in there. So what you want to do is you kind of want to squeeze the ends together until they become a little more up and down instead of flared out. And I like to do that against a table. Kind of show you how I do it. I like to do it on a mat or something that's not wood or can conduct, because you don't want to get static and have it. But you put it there and then you just kind of bend it forward. And then put it down on the other side and just kind of bend it forward. And then that kind of makes it a little more up and down. And if you bent it too far, don't worry about it. You can kind of pull them apart a little bit with your fingers. And yeah, you can get a chip. Looks like that. So let's go ahead and put this on. Now you want to be able to have a nice line that goes from where power and ground to the top and bottom of your chip. So this would be okay because you have a nice line from where the power goes into the chip or the ground into there. But if you had it, let's say, up a couple more, now you can see that there's, I'm not quite sure why they did that on the breadboard, but like there's a gap here between where the power and ground is, so it would have to kind of have this awkward angle, and it makes it kind of hard to figure out what's going on when you're running wires. It gets kind of ugly pretty quick. So I would recommend putting it down right about there. Maybe have it go into pin 7 or 8 and the bottom go to 11. So 8, 11, that's a good spot for it right there. You have a nice connection to your ground. Looks a little cleaner. So pin 1. Pin 1 is your top pin here, up here, and that goes to ground, but in between the ground and your positive, which is pin 8, you want to have a capacitor there. So I'm gonna show you, even though the schematic shows this right here where it kind of like jumps between them. So you would think, oh, I want to put a capacitor like that. You're like, let's do that, which totally works. It's fine, but it gets ugly if you start having wires go above and over your chip, and it can get hard to diagnose what's going on. And essentially what you're trying to do is smooth out the supply voltage coming through. So here's a little trick in this case. Just put your capacitor and have it go right between positive and negative. Like that. There you go. Right there. And what that'll do is it'll smooth out any voltage inputs that you have, which is nice. Okay. So, if your board looks like that right now, you're doing good. Now, we're going to want to get our polar capacitor, and we're going to want to connect up pin 2. Oh, I'm sorry, we forgot to ground pin 1. So, let's do that. Now I have little kits like this that have wires in there to make it just a little cleaner when I'm wiring things up. Pin 8. Trying to do this without blocking your view, and it's not the easiest thing to do. There we go. That's good. Let's. There we go. So you have that looking there now. So that's good. So now we're going to move on to pin 2. Pin 2 is going to have our polar capacitor. Now what I like to do with that is I like to move it, bend it, and kind of do that. It puts them in a little more of an even situation. Again, you're looking for this to go on the ground side, like how this wire is plugged in the blue. So, grab it, put it in there, like that. Put in the negative on the negative sign, and then goes into pin 2. Excellent. Now, we need to connect pin 2 with pin 6. We need to get, we want to connect it from here. Connect it from here, bring it over, and connect it to pin 6 in front of the potentiometer. So, let's go ahead and do that. Now some of you might have different cables. In fact, I'm not 100% sure where I put my other ones, but if you have wires that look like this, you can plug it in there. So let's say that we put it into pin 2, in between the capacitor and pin 2, and then brought it over to 6. So we know that that goes 1, 2, 3, 4, 5, 6. What in the world? Sorry guys, I don't know what that sound is. I apologize if you can hear that. I think somebody's car's about to blow up. Anywho, yeah, you can do that. Or maybe you have a little bit of a different wire that gives you a little more flexibility. Maybe you have something that you made so it has the ability to kind of move around a little easier. So we know that that's pin 6. And then we have it fold over, go to pin 2, something like that. I don't know. You can have it however you wanna do it. Whatever makes it look a little cleaner for you. So we have pin 2 done. Pin 3 is our output. Now I would recommend having a wire for pin 3 to come out for your output. So now you know that that's your output. That's going to go to whatever, and it makes it a little easier to do. Now pin 4. Pin 4 goes to a positive. So I like to use red or yellow or orange to signify my power. Those colors tend to stand out a little better. So what we'll do is we'll pull that out of pin 3 for now to clean it up, and put this in here like so. There we go. So you have red going to pin 4, which is nice. Yep. Pin 5 is our other capacitor that goes to ground. So we're going to go ahead and grab our other capacitor here, put it in negative, and connect it to pin 5. That easy. See? 5 in ground. Pin 6 is our variable resistor. Now, that one, what we're going to do for this here is our variable resistor. Is I like to use the middle pin, the one by itself, as one end, and the side that's on the top in this orientation here. I don't know if it'll stay in that orientation. Sorry guys. So, in this orientation here we have the flat side. If that's facing my right, I call this the top, and then the middle, and then the bottom. So on the top we'll have it connect up to pin 7, and also our 1K resistor. And on this one we'll go into pin 6. And then the bottom one won't be connected at all. Now, depending on how you're wiring it up here, it might be better to put the resistor just kind of down here, because it'll make it to where you don't have to worry about connecting up the pins, because you don't want to have it run into this pin and it makes it a little cluttered up there. So what we'll do is we'll put it in here, and take that one and we'll go to pin 6, which is up here. Pin 6 there. And then we'll grab another one. And you can use whatever color wire you guys want, whatever you have available to you. It really doesn't matter. Tend to usually use yellow, red, and orange as power. I like to do white as an output and use blue, green, and black as ground. But blue and green are also common, like data cables. So, whichever you'd like there. So, we had that go to pin 7, up here like that. Now we want to have the RA, the resistor, 1K resistor, this one, go from pin 7 here to positive. So we will do that right now. Right there. See that? There you go. And then the final one is we will go put in our supply voltage in the pin 8, which is up here. Which looks like that. Right there. There we go. Now, you have a clock, but you have really no way of knowing what's going on because we can't physically see what's happening as the clock turns on. Well, now we're going to grab another 2 items. What color should we do? Red, blue, green, blue? Thinking blue LED would be cool. We're going to grab a blue LED and a 200 ohm resistor. Now it doesn't have to be 200 ohm. It can be more than that, a little less than that. But basically what we're going to try to do is make it to where we don't have too much current flowing through the LED and the LED burning out. So, the LEDs will tend to have 2 pins that look like that, one longer, one shorter. The longer pin is your positive, and the shorter pin is your negative. Anode and cathode. I always forget which one's which, but yeah. So we're going to do the longer pin, the positive side, and connect that up to the pin 3, our output. So where we have that wire for pin 3, we'll plug that in, and then we'll just bring it down here. Plug it in like right there. Why not? Now we'll take our longer end and plug it in on the one that runs along the white here. So we'll go like that. There we go. See? Like that. And then we'll go to the ground and have the resistor go between the ground and the LED. Kind of like that. So that allows current to flow through the LED, which is great. Now, I want to connect up the positives and negatives together. So, what I like to do is at the bottom of the board, grab one on positive and then connect it to this positive. So they're connected, so red and red are together. And then I like to go blue and to the other blue. So that makes the grounds and the positives on both rails equal to each other. So they're good. Boop. Like that. Excellent. Okay, now we need to power it up. So, I have a power supply up here. I am so sorry, you guys, for the wobbly. I'm sure it's going to drive you nuts. I have a power supply here. And it's set right now for 5 volts. Right there, 5 volts. And we have a red lead and the black lead. So this is our ground, and this is our power. And we're going to connect them up here at the top of the board. There. Alright. So, have our positive come in here to positive. And then have our negative come here to our negative. LED should turn on. Hey, look, it's blinking. Question is do we even know how fast it blinks? Like, what did we calculate here? What kind of resistance are we looking at? What's causing it to blink at this speed? What happens if we adjust the resistor, the variable resistor here? What if we spin it one way? Let's see if I can get it. What way is going to be the best for you to see? So if I spin it one way, oh look, it starts going way faster. Whoa, sorry strobe. Should have told you. You go the other way, it slows down. Almost way too slow. So what's going on? How do we know what it does? Well, this is the beauty of an oscilloscope. The oscilloscope will let us hook up and see what we did. What did we calculate? We can also use another tool, which is a voltmeter, and this tool right here. This tool allows us to measure the voltage, the ohms, the capacitance, the frequency, the duty cycle. Oh, you know, I've never tried that one. Should we plug it in and see if it does that? See how close it gets to actual oscilloscope? That'd be kind of cool. And it does your temperature, so how hot things are getting. HFE is, we'll talk about that later. And then you have your current, your amps. Yeah, so that wasn't very expensive. I won't say I paid $30 for that one on Amazon. Don't have an affiliate link. I'm not trying to make a bunch of money off of this, so not worried about it. Anyways, so at this point you've built a clock. You have a blinking LED and it turns on and it runs great. Let us see if this can really calculate the frequency. I've never tried it. You know, it's weird. I've had this for this whole time and I've never seen it work. So there's the hertz. And so what I'm going to do is I'm going to connect it to the output and ground. And we should theoretically be able to see what it's at. So, output. Or the input. That's the input, and then the ground. Here. Maybe we don't ground it? I'm not sure. I think we need to ground it. Let's straight to the ground. See if that... So that doesn't work. Huh. I wonder how this function does it. Oh, did you see it? It changed for a second. It said 0.8 hertz. Which it's blinking at... It's close to 1 a second, right? 1, 2, 3, 4, 5. Yeah, it's pretty close. Which would make sense. It's almost 1 hertz. 0.8. A little slower than once a second. I think if I select it, I can change. Maybe it'll give me a period. Maybe not. Oh, here's the duty cycle. Is it 50-50? Hey, look at that. Almost 50% duty cycle. 49.2. Wasn't that what we were looking at in our math when we were calculating the two? So obviously that means that our potentiometer must be very close to that 860K resistance, which is pretty nice. Well, you know. I don't know what it is because I haven't really measured it. Now, we should try to check out to see what the resistance value is of it. So what we'll do is we'll pull off our leads here. And the way that we test the resistance is we hook it up to the end of one, and then hook it up to the other side. And then we switch it to the ohm symbol. And oh, you have to have it kind of hooked up. We're not running the voltage through it, because that is messing it all sorts of up. Anywho, if you wanted to hook it up, you would be able to do it, but you should do it when you're not running voltage through it, if you want to measure the resistance of it. But we'll just leave it as it is for now, because we're going to want to hook up the oscilloscope and watch the frequency of everything. So let me come back here. Alright, so you physically built your clock. It's blinking. You maybe have adjusted your potentiometer. If you don't have a variable resistor, knowing the math that we did in the beginning of the episode, you saw how to calculate everything. Do that and find a resistor that's as comparable to it. You know, maybe you have a 680K ohm resistor. You got a kit, and that's one of them. Use that instead of a variable resistor. It'll set it at a set frequency by your math with that. You can't adjust it, unfortunately, but you can always switch it out with a different resistor and play around with the math to find a frequency that you like. And when it comes to us building this computer, you'll be able to kind of either one, order a kit, they're not very expensive on Amazon, and get one that allows you to have a variable resistor, or two, find one that allows you to have that frequency that you want to keep, and use that resistor and just have it permanently set at that. And that's not a big deal either. And we'll figure out what frequency we want when we work with this computer. Also, another thing is when we want to start diagnosing how things work, we're going to put in a switch that allow us to switch in between having the clock go at a constant rate, or stop it and then pulse through it at our own rate, so we can kind of diagnose and examine what's going on in between each clock cycle and if our computer is operating correctly. So that's good to know. Alright, so let's do the oscilloscope, shall we? let me bring up waveforms. And we'll put it on scope. And we'll go to desktop. Here's our waveforms. We have channel 1, channel 2. And kids with their cars. We have our set seconds and our base for where we want everything to go when we want to run it. So now we gotta hook it up, and I have to remember which ones do what on here. Okay, I think it's the yellow and the black. We will find out here in a second if I'm right, because I gotta hook it up, put it in. So click run. And we want to have this up here at 5 volts. That's a little much. Let's do 1 volt. There we go. And it'll come up here if it goes high. So apparently that was not it. Apologize for that. I should have probably looked at the documentation to figure out if this was it or not. Oh, I think I got it. Let's put in the ground. Okay, it's running a little fast for us, right? Because here we go. There we go. Look, it's reading it. What are we looking at? 800 hertz, which it said on our voltmeter. We got about 800 hertz, and that's what, almost a second. Does this show our period here? Well, we know our period is from here to here, and this is 1 second and a half, so we're about 1.5 seconds is our period at about 800 hertz. Wait, no, it should be like 0.8 hertz. Oh, 8,000 samples at 800 hertz. Huh. Okay. Let's see here. Will it show us? So I normally do measurements, data, measurements. We're kind of learning this one together. Let's see. Let's stop it here. Let's add in a measurement. Horizontal. Frequency. You seen this? Period. Add in period. Close. Ah, look at that. We're looking at about 1.19 seconds. I don't know if that's something you can see. Is it clear on your end? I hope it is. Yeah, we're looking at about 1.19 seconds. And so let's add in another. Let's do frequency. Look at that, 0.9. So almost 1 hertz. So yeah, it was blinking at a pretty constant rate, and this is what we're looking at here. Now, what I could do is I could hook up the other blue channel and show you the capacitor and work in there that way. But we'll go ahead and show you how to hook it up so you can see from your oscilloscope what you're dealing with. So we'll change the view here to the circuit. So I'm using a thing called Analog Discovery 2 by Digilent. Hope I pronounced that right. And we used the first wires, and we did our ground, and then we probed the end that is at the output. So every time that light turns on, it's showing a pulse high, and then it goes up onto our screen and gives us the ability to see the oscilloscope. So those are the 2 wires we plugged in from there. Ground and then our output on the IC chip. So there it is. There's our oscilloscope. There's our proof that shows that our math is right. Now, let me go ahead and find out what the resistance is of that resistor, and we'll know if it's around 680K. We're looking at what we want to look at, right? So let's bring that up and take this out and drop everything, because that's what I do best. So the power's out. Pulling out the resistor here. Pulling that out. And let's switch over to circuit scene. There we go. So we have our 3 leads here, and we're going to look at the top and the bottom. And we're going to bring in our voltmeter. I guess the nice thing about YouTube is, you don't have to see all the things you do in between to set it up. So I haven't adjusted anything on the resistor. I haven't twisted it. So we're gonna go ahead and hook it up onto those 2 lines. Look at that. We're looking at 0.826 of a million of an ohm, which is about 825K, and we said it was going to be about 860K. Wow, we were pretty close in the long scheme of things. So yeah, our math worked. What do you know, guys? Our math worked. That's awesome. Well, this is about to wrap up our day. I think we did really good. We built a cool circuit. We saw the LED blinking. We learned a little bit about math. We saw how the formulas played out. We calculated tau and our high and low and figured out what our duty cycle is. We learned what a period was, what frequency is. And we hooked up an oscilloscope and we saw it go from high to low and visually saw an image of everything we went over today. So the last thing I want to show and talk about is percent error before we go out, because I want you to do this. When you go and you build this, it's one thing to plug in the resistor that says it's 1K, plug in a capacitor that says it's 1 microfarad and all that. But when you're doing this in a lab-based setting, when you're trying to do this on the educational end, on when you're doing this as a soon-to-be engineer at the university or college level, you need to understand, well, my math was close, but it wasn't exact. I wanted to get 1 second, but we got 1.1 second period. Why is that? If you could understand and answer those questions, then that's how you become an engineer. You need to know, why does that work? What is the whole point of it? And that's where I'm going to show you. I'm going to show you percent error. We're going to scroll on up here. So, percent error, did I write it out? Hope I did. I may not have. No, I didn't write it out. So, percent error is your expected value minus your experimental value. It should be what you got out of it. So, let's say we did our calculation and we expected to get out 1 second here. In fact, why don't we use the numbers that I have here? Let me go here real quick. Boom. Here you go. So this is our percent error. This is where we figure out how far we were off, and then we can kind of figure out at that point why we were off, and see if we can kind of figure out as an engineer what we were off by. So this delta symbol, or is percent error. VA is our actual value observed, so that would be our 1.1 on our oscilloscope. Expected value, that would be our 1 second, what we were hoping to achieve. So you do what we saw minus what we were hoping to get divided by what we were hoping to get. These two bars right here are called absolute value. So if this became negative, let's say that what we wanted was a lot bigger than or a little bit bigger than what we saw, then we'd have a negative value here. But you can't have negative off, but you can have positive off, percentage off. So the absolute value just kind of negates that negative sign. It just says, go away negative, we don't want to play with you today. So let's do the math on that. I'll switch us over to circuit view, and we'll look at the math. We'll do it together. Oh, I never put the cap back on this. I hope it still works. So, our VA, our observed value was 1.01? No. I think it was 1.109 seconds. Our value that we were expecting was going to be 1.00 seconds. Let me double check that real quick, gentlemen and ladies. Okay. Yeah, it was even smaller than that. There was another 0 in there, but I'm not going to worry about it. So we know that our formula is absolute value of 1.109 minus 1.00 all over 1.00. And then you multiply that by 100, because when you have 100, you can take that small decimal you're going to have and make that into a percent. And that equals our percent error. I call it PE, P_E. So we know that if we subtract 1 from that, we got 0.109 over 1.0. And we don't really need the absolute value anymore because it's not negative. We have a little bit more than what we thought it was going to be. And then that little number right there is it is what it is. It is over 1, duh. So we have 0.109 times 100. And then that just goes 1, 2. So we were 10.9% off in this equation. So that's our percent error. That's our PE. Our percent error is 10.9% off. Sounds like a lot. I mean, it was off by a bit for the small numbers we're working with. But yeah, it's not too shabby. But why were we off by 10.9%? What made it off by that much? We used the same stuff. Well, as we saw, we were expecting our value for RB to equal like 686K, right? But or was it 860? Am I already messing up? What was it? It was like 868K. Wow, dyslexia. Okay, I'll tell you, if any of you have dyslexia, like legitimately have it, switch numbers around or do whatever, it is rough at the higher level math. Those are like the most stupid mistakes to make. And if you let your instructor know in the school and they can see the patterns of when you do that, and that obviously you know it, a lot of instructors are cool and they'll work with you, but not all of them. So just try to be really good at double checking your math. Take your time. You know, you can always go to disability services. They'll give you extra time on tests so you can go through and be like, did I switch 2 numbers around? Did I put a negative when it shouldn't have been negative? Did I put positive when it should have been negative? All that kind of stuff. So we know we wanted that to be our number when we calculated it, or around there. And what we actually had was like 826K. So we know that you could do the percent error with that. This is what we expected. This is what we measured. We do the percent error, we'll see how far we're off there. That's one to say, hey, this is what we're off by. Then we could do our capacitor. You know, I bet you money, instead of being 1 microfarad, it's actually probably something like 1.5 microfarad. Which would bump it up, make it a little bit faster. So, and then you could do that percent error on this one. And then you could do the 1K resistor. And I bet you it's actually sitting there at like 998 ohms. And you could do the percent error there. And then when you do the percent error on this one, and you take them and you add them all together, PE1 plus PE2 plus PE3, I bet you it'll get pretty close to looking like this one. I bet you it'll be off by about 10.9%. Or really close to it when you add all those together. So give it a shot. See what you think. See if you can come up with a reason for it. Your resistance might have been off in reality. The capacitor might have been off by something. But also know that the world isn't perfect. Nothing works exactly as it does in the formulas. They're close, they are, but you have, resistance in the wires. The breadboard connections may not have been super strong. The LED was drawing current, which then could have changed how much the capacitor could discharge to slow it down by a little bit. When you start getting at the real micro level or nano or pico, things change and noise comes into the circuit. So it will never always be perfect, but it'll be close. And so you should always be close. You should be able to figure out, hey, this circuit's going to operate in this manner, and it could be off by a little bit here and there. And if you have at least some good ideas to know why it's off, we know that some of our resistance was off. We know that potentially some of the capacitance was a little different. And when you do all the math, you can figure out that's why. In fact, when I was doing the desktop view here on this, I was calculating the percent error, and using our original values, I figured out what our percent error was like 8.45%. That was our expected. And then this was the measured values, and even that was still off by like 2%, almost 3%. It was a lot lower, as you see here. So let me explain what this was. This percent error here was using the expected values from my calculations. I was using 1K, 100K. I was using exactly 1 microfarad. And if you calculated it out, here's your period. Here's our period of 139.293 milliseconds. And then this is our period with the actual values I measured. 998 ohms, 100,400 K ohms, and a little bit more than 1 microfarad. And then that gave me 146.838 milliseconds compared to 139. Not a huge difference, obviously. It's really, really close, but you can see the difference. And so then when I'm looking at 150 to 152 milliseconds on my oscilloscope, well, now I gotta figure out, okay, well, how far am I off? And I was off by 8% on just expected values, but I was only off by 2%, almost 3%, with the measured values. So you can see, as an engineer, I was saying, hey, look, these parts aren't perfect. They're not exactly that. Let's find out what they are, and we can justify why are off by a little bit. But at this level, it's really, really, really low. Nothing to worry about. And so I went over frequency and measured it on the oscilloscope. And this is kind of what I do, you know. And here we go. What I want capacitor 1 to be, what the actual value measured was, and I write it all out. Really, C2, C3, you don't even have to worry about that. And that just lets you kind of figure out, hey, I'm expecting to get 1 second. This is what it should be. What you get. So that ends our show for today. I hope you took something away from it. I hope you learned to be a little bit of an engineer. This is kind of what it is to explore and design as an engineer, and what goes into it. Some math. And you learned what a circuit was about, and how it worked, and why we chose the values we did for our components. So if you have any questions, leave them in the comments on YouTube, or I guess, I don't know, if there's a way to message me, PM me on Twitch. I guess that's always a possibility. I'm sure you all know how to use Twitch more than I do right now, but eventually I'll learn it. And we'll be back again to start building the next section, which is our debounce, and allows us to put in our switch to manually have the clock turn on and off. So get ready for that one. That'll be fun. Alright, I'd like to thank you all for showing up. I'd like to again thank Ben Eater for putting up this information for me to kind of take from and start kind of building our class and stuff around it. And hope you enjoyed it. Stay safe out there. You're all great. It's great to have you on the Twitch family, and we will see you next time. Bye now.